It's a great occasion for us to meet and listen to one very interesting lecture from Prof. Biswas. He's a product of IIC, and I learned many things during my research days under JV from electrical engineering. Probably he's one of the best power electronics engineer ever produced from IIC. Extremely good, extremely passionate about hardware design. Go deep into this one. Very good teacher. So that you will understand now. Our association is close to 46 years. Starting from 78. From he left his PhD, and he's one of the first person who extensively done in current source inverters research. His initial works are in textbooks now. Okay, later he moved to Jadavpur, started teaching research there. He's still active. Probably many power supply manufacturers across the country or battery chargers across the country will have one of his design in their product right from the beginning. So I request Professor Biswas to give his interesting lecture. Come.
Thank you, Dr. Gopakumar, for the kind and passionate introduction. Yeah, I love this place still, although it's been long, 46 years that I had come down here first. When I had come down, there was no connection, straight connection from my place. I come from Calcutta city, no connection. We come down to Chennai, change trains. There were no flights up to this place and come down. I mean, those days were different. In IIC campus was different, okay, entirely different. So those are old stories which we can talk about later on. Yes, regarding products, yes, I have somehow had the passion, but very frankly, Professor Joseph Vidyathil gave me the platform to experiment with my own hands and learn. He always had taught me that if you're doing a work with hardware, if there is something damaged, just don't worry. Think and think again what went wrong. Don't worry about what is damaged. What went wrong, and try to rectify that. And that way you will learn. So with his blessings, I have started out with various industries in the country. And today some of my designs are already running in the trains, on the locomotives. Some of my designs are on the standby power supplies beside the track. I don't know if many of you may not be aware, with the signaling equipment and the other communication power supplies. Some of the large equipments that I designed right from scratch are for aircraft applications, naval submarine chargers, and we are now making hydrogen rectifiers. Large ratings, more than several megawatt rating. Okay. So let's start with the lecture itself. So as I have indicated here, practical selection, design and interconnection of components for power electronic systems. I was assigned a 1 hour lecture slot. I said it can't be done because this is a 1 day lecture. So anyway, I try to condense and I'll try to skip some of the relatively irrelevant areas. So we start with the resistance. We all know what a resistance is, but when you look at the resistance, simple resistance where it's not like that. Inside there will be a definite value of the resistance, there will be some inductance, and there will be certain capacitance across the two ends. And resistances are designed, used in power electronics to dissipate much of the energy from trapped energy from other components, etc. But they are not ideal, considering that we are looking into high frequency switchings, not considering DC applications. This slide will show you types of construction of different types of resistance. This is a carbon composition resistance where you have a composition material between the two ends, metal caps, and the composition mixture decides the resistance value. This is a straight rod-like structure, and hence there is hardly any inductance. Inductance is very small. Inductance is something that's associated with the flux. So whether it's a straight line or a coil, it doesn't matter, you have inductance. As long as current is flowing, you have flux linkage, you will get inductance. The only thing is when you make it into a coil, you have much more mutual coupling between the turns, so your total inductance increases. If you have a straight line of that wire, the inductance value is less. They are used only in very specific applications because of the reason you cannot make them very accurate. 10% accuracy. Everybody today wants 1% accuracy of resistance. So they are used in very specific applications. Even today you will get them. Next comes the film resistance, carbon film or the metal film. There we have a ceramic base tube and you have a metal deposition or a carbon film deposition and you etch out a part using a laser. So you have a precise value of resistance that formed because it's consisting of the width of the laser cut and the number of spirals you make. But the moment you make spirals, you land up with more inductance into it compared to this. And of course you have your wear-wound resistance, which is going in, if you look inside it, it has a wear going round and round. So external appearances may be like this. This is our typical film resistance and wear-wound resistance. You see the difference, it has more inductance. The capacitance comes only at very high frequencies because of the space between the two ends. You have potential difference across the resistance separated between them, so it forms a capacitance. It may be low, yes, it may be in nanofarads or picofarads, but when you are operating at high switching frequencies, that capacitance actually bridges the resistance and the currents try to flow, part of the currents try to flow across. So that's how we try to understand the behavior of the resistance. Now we move on to the capacitor. If this is your simple capacitor, inside it you will have a resistance, a series inductance, the actual capacitance and a shunt resistance. The shunt resistance is because of the dielectric loss of the capacitor. No capacitor is ideal. Its dielectric has a loss which you can express in terms of tan delta. So it has a loss. So that is represented by the resistance in shunt. The series inductance comes from two components. One is if you roll and form a tubular capacitance, the foil is rolled so the current moves in loops. So you have an inductance because of the foil path. Second is the leads. They themselves also create inductances. As I said, anywhere there is a current flow and there is a flux linkage created, they will create inductances. And the resistance is the resistance, physical resistance of the path of current flow. Now, if you look at this equivalent circuit and we try to replace it by a total series equivalent circuit, it becomes this. This is called as the ESR or the equivalent series resistance. This is called as the ESL or the equivalent series inductance, and this is your pure capacitance. Series RLC circuit now has a resonant frequency. That's where the catch starts. That's where the catch starts. So you can find out the Z as expressed as ESR plus JW ESL minus 1 by omega C. So you have a resonant characteristic, series resonant characteristic, and if you plot Z versus the frequency, this is the type of curve that you get. It comes down and then goes up almost linearly, and we know that at the resonant condition, its equivalent is the ESR, the resistance part. Then the main question is, in any resonant series resonant circuit, below resonant frequency, the circuit behaves like a capacitor, and above resonant frequency, the circuit behaves like an inductance. So therefore, your capacitance, if you are working at a frequency which is higher than its resonance frequency, it's useless, it becomes inductive, even though it's a capacitance element that you have selected, a commercial capacitance. It's of no use at that point. And the catch is here, if you look at the expression of resonant frequency 1 by twice by root LC, so higher value of L makes lower value of resonant frequency. Higher value of L will be created by rolling the capacitor more and more, typically like in an electrolytic capacitor. You try to make a compact capacitor for a large microfarad, so the roll is going on, you have a huge length of foil, you roll it up, so the current flows along that roll, and you land up with a higher value of ESL. So you land up with a higher value of ESL means you are going to have a lower resonant frequency. So that means your capacitor becomes useless after several hundreds of kilohertz. So to overcome that, very often you will find in your power supplies, as an example, a 10 microfarad electrolytic capacitor shunted by a 0.1 microfarad ceramic. You might wonder what's this small value 0.1 microfarad going to contribute to 10 microfarad. It's a small amount. Why do we put it? It's because if you look at this characteristic here, the electrolytic capacitor characteristic is the first one in dark that I've shown, and the 0.1 ceramic is in dotted that I've shown. So you will see the electrolytic has a lower resonant frequency, but the ceramic, because it's simply two plates separated by a dielectric, no roll up, has much lower inductance, so it has a higher value of resonant frequency. So if you are working at the frequency F1, your 10 microfarad is going to give you the most of the capacitive effects. But as you shift on to the frequency F2, you are already in the inductive region of the electrolytic. That's not going to help you anymore. So if you have a 0.1, a small value of capacitance, it can give you the same impedance because of the higher frequency. You don't need a large microfarad value because you are talking about the higher frequency effect. So even a smaller value of microfarad can help you do it. So if you have the combined effect, you have a coverage of capacitive effect over a large range of frequency. That's why even in power supplies, decoupling, your bus bars, everywhere we use not only electrolytic, we have to use some sort of a low ESL capacitor, maybe ceramic. In power we don't get that rating ceramic, so we use special polyester capacitors which have low ESL. Low ESL is created by having multiple tap-offs from the foils. Instead of having a tap at one end, you have multiple tap-offs, so you have multiple feeding points for the current into the foil, so you get low ESL capacitors. This gives you a look into the typical structure. Here you can understand this rolled, and so you get an electrolytic capacitor, why you get a large amount of inductance and why the resonance frequency is low. These are electrolytic capacitors of different types, tantalum, aluminium, electrolytic, etc. And here you take a look at the non-electrolytic capacitor. Ceramic is one of the best in terms of decoupling, but not one of the best in terms of timing, because these capacitors have a variation of capacitance with temperature. So they are not going to be stable. Value will not be stable with temperature, but decoupling value does not become an important factor. The next best will be your polyester capacitors, either in this form or in the axial lead form or in the box type. In the axial lead, you will note that at one end there is a black line. That black line indicates the outer foil. That's very important in particularly EMI, because when you place a component, let's say vertically for the time being, if the outer foil is having a variation of voltage, that's going to radiate EMI all over the PCB area. But if the outer foil is at the electronic ground potential, that's at a stable potential. So it's essential to identify which end is the outer foil. If you have the box type, if it's a good manufacturer, he will also put a straight line across one of the ends. That indicates the outer foil. So the outer foil should go to the electronic circuit ground so that the minimum change of potential is there. That way you can reduce interferences within your circuit. For ceramic, there is no outer foil. It's just two plates separated by dielectric. How do you make the connections, capacitors, to your PCB lines or bus bars? This method shows that you have a capacitor placed at one side and you have brought two wires from the bus bar or the PCB track and made a connection. This is incorrect because we are talking about ESL and ESR. This length of the wire connection itself adds on to your ESR and ESL. So you have a problem with it. But this is the correct method where the two ends will come and terminate on the terminals of the capacitance and then proceed. So the capacitor connection wise has the minimum ESR and the minimum ESL. Then you get the best out of the capacitor connection. We often have to put capacitors in parallel because it's not possible to operate without capacitors in parallel, because you may need a large microfarad and then you don't get that value for various reasons. Even if a value is available, the size may be big and you can't put it into the box, so you take a lower height and you put multiple. So this is one method of making a parallel connection, but it's not correct. Why? Because you see, between the middle capacitor, the length of the wires is the minimum, and the two outer capacitors have a relatively larger length of wire. So therefore, when there is a AC component of current flowing through this, most of the AC component of current will flow through this rather than through the inductance and resistance of the outer capacitors. So invariably you can feel that this capacitor becomes hotter than the others. They are not sharing equally. And if you there are many ways of making a relatively balanced. You can't get a perfect balance. This seems to be one way where you'll find that every capacitor traverses more or less the same length of wire. Here you have one length plus two length for the lower arm. Here you have one length or two length for the upper arm, and the middle also has the same. You're trying to make a balance of the lengths. It's not possible all the time to do that. Sometimes you may have to add capacitors on the bus bar straight away like this. Depends on your layout and your components, your total equipment structure. In this case, you'll have definitely the capacitor which is closest to the ripple producing source will definitely carry more ripple current, and you can feel that capacitor is becoming more warm than the others. Now all your capacitors must be provided with cooling, and parallel connection of capacitor gives you more surface area available for cooling. For example, as an example, maybe I need 100 microfarad. I can get one single 100 microfarad capacitor, and at the same time I can use say 50 microfarad, two numbers in parallel. I will prefer to use two numbers of 50 microfarad in parallel because the surface area available for each of those cylindrical structure is much more compared to a single capacitor. Why am I worried about surface area? Because cooling. Every capacitor has a permitted ripple current capability inside it. Depends on the losses inside it and the temperature rise that is permitted within the foils. Otherwise, there will be a failure of the dielectric inside, and the capacitance value can deteriorate over time. Electrolytics are one of the most prone to failures. So therefore you have to be sure about the amount of current that you are permitting. At the same time, if you want to make a filter out of the capacitors, you must know what is the value of ESR inside it. Without knowing the ESR value, you can't make a filter, because when you're trying to make a LC filter, if you calculate with a L and a C only, you're assuming an ideal C. So fine, through the ripple current through the C gives you a particular value of voltage drop across the C, which is the ripple at the output. But no, if you have a resistance in series, the resistance will also have a drop, and the drop across the resistance and the capacitance are in quadrature. So you will get a longer length of voltage drop. You might ask me, what is the importance of maybe a milliohm of resistance value ESR? The importance is the relative value. When you're looking at the capacitance at the higher switching frequency, its capacitive reactance becomes very, very low and can become comparable to the value of resistance ESR that's inside it. So if they become comparable, your calculations will go wrong. So you must know what is the value of ESR to make a proper prediction of the value of capacitor you are going to use. And therefore, if you use parallel capacitors, ESR will become in parallel and will get reduced. So that is second advantage of using capacitors in parallel instead of a single capacitor. Capacitors are often connected in series. For example, if you have a 600 volt DC bus, we normally don't get electrolytic capacitors in more than 450 volts normally. So we have to connect in series because 600 is a nominal. It can go up still further. So we have to use it in that process. Yes, the effective ESR and inductance is increased, and voltage balancing depends on the tolerance of capacitors values. So sufficient margin in voltage is required. Electrolytics have a 20% tolerance in voltage, and God forbid if one is at the bottom is minus 20 and the other is plus 20, you don't know. It's the actual value irrespective of the nameplate rating of the capacitor. You buy a 20 microfarad capacitor, then you measure and see exactly how much it is. It will be varying. 20 is the nominal nameplate value. Plus minus 20% is the typical tolerance that you can get. So when you are making a series connection, this is the right way. You put the capacitors in series and then put them in parallel across the bus. Why parallel? Because when you put in series, the effective capacitance becomes half. So you have to compensate for the need of total microfarad. So you have to compensate by putting parallel branches. But if you parallel the capacitors first and then put the two banks in series, you are making a mistake. Because if one of the capacitors in that bank blows out for some reason, you will have a huge unbalance. You can see now you have two capacitors on the top and three at the bottom. So midpoint voltage will shift drastically and you will have a cascaded failure of all the other capacitors. So that type of connection should not be done in the middle. Leave them alone. So if one capacitor here blows out, let that limb blow out. The others are not going to get affected. When I use the word blowout, it does not always mean that it's going to really make a sound and blow out. It may just become non-functional. It may become leaky inside. For example, our fan capacitors often become non-functional. So if it becomes non-functional, you are still saved in this case. Okay, we move on to magnetic components. We have transformers where we have power frequency transformers, we have high frequency transformers, we have unidirectional excitation transformers, and we have flyback transformers. Flyback transformers are really not transformers, they are coupled inductor. Why? Because the secondary voltage is not always defined by the turns ratio, is defined by the energy amount that is sent there. So they are not exact transformers in that true sense. And we also have inductors or chokes, whatever you call them, AC applications, DC applications, or power factor applications where you have a sine wave superimposed with harmonics. Power frequency normally implies 50 hertz, 60 hertz, and 400 hertz. 400 hertz is used in all aircraft applications, even in this country. All the commercial military aircrafts, they all operate at 400. So what is the use of the transformers? They have to be checked on the ground before they are made airborne. So for checking, 400 hertz supply is required for them. So we have something called as a GPU, a ground power unit, where you have a 400 hertz supply. It goes and gets plugged in, and you check all your navigation equipment and other communication equipment before it's ready to go off. High frequency transformers can be anywhere from 20 kilohertz up to 1 megahertz, anything in that range. Unidirectional excitation transformers are where the voltage traverses only one direction. There is no AC really in that sense in the transformer supply. And I said flyback, okay. Okay, we can skip this. I think most of you know what transformer is, leakage inductance, why it comes, and so on. This is some of the typical modern transformers that we have. This is a high frequency transformer, toroidal. This is for PCB mounting. These are large power transformers, 3-phase, and so on. Okay. Come to the basic equation of a transformer with an alternating voltage. So I start with small e is equal to n d phi by dt. I have eliminated the negative sign because it's a question of how you want to see the voltage, as an induced voltage or a voltage drop. Both ways you are right. It's not a problem. So your vector diagram can be drawn anyway. As long as you stick to one particular concept, it's okay. So E is equal to n d phi by dt, and if I assume that flux has to be sinusoidal, then if you put phi is equal to phi m sin omega t, you can show that E is equal to omega n phi m cos omega t. Fine. So there's a 90-degree phase shift between the flux and the voltage, and we find that both are sinusoidal. That means if you conversely, if you apply a sinusoidal voltage to a transformer, your flux is bound to be sinusoidal. So your magnetizing current is bound to be sinusoidal. Power transformers in many applications, 50 hertz transformers, do not have a sinusoidal no load current, but for a different reason, because the flux density in those cores are operated beyond their knee point. So as a result, it's not in the linear region of BH curve. That's why the no load current develops harmonics. But if you are able to operate within the knee point of the flux density curve, you will get a perfect sine wave in the no load current. And then you can proceed to show that the conventional equation ERMS is equal to 4.44 F N BM into AC. This is a very common expression for sine wave. Now let us take a look at flux reset in unidirectional excitation transformers. That means where the transformer is provided only with a voltage pulse ED up to this point. We'll consider only T on for the time being, that duration. This is a DC applied, and many people think that if you apply DC to a transformer, you don't get a voltage on the secondary side. That's wrong, because you still look back at your expression of E is equal to n d phi by dt. If you have faith in this expression, the left hand side, if I make it DC, it means constant. The maths tells us that the right hand side is constant, if the maths is correct. I have made it left hand side constant, so the right hand side becomes constant. If the right hand side is constant, it tells me that d phi by dt is constant. So it tells me flux rises up linearly. This is the thing, d phi by dt is constant. Flux goes up linearly. It doesn't say that there's no change of flux. That's absolutely wrong. There will be a change of flux. So the flux rises up linearly. And if I say that E is, okay, this is what I told, d phi by dt is constant. And if I say if E is 0, then it implies d phi by dt is 0. So making the voltage 0 does not ensure that the flux has become 0. D phi by dt is 0 means there will be no further change of flux. Flux will remain where it was ideally. So you have to understand the interpretation of the waveforms, and that's exactly what happens. So when we apply a DC voltage to a transformer, the flux rises up to a value of phi m, wherever you want, depends on the magnitude of voltage and the time you have applied. And if you make it 0, flux will remain at that point. So you have to bring the flux down again. So bring the flux down, you have to apply a negative voltage there. So if you apply a negative voltage, the flux comes down with a minus E, and so you can see minus d phi by dt. It will come down, and you want to ensure that the flux is 0 before you start the next pulse. If the flux is not 0, the next pulse will start from here, and there will be a staircase saturation of the flux. It goes up and then comes down slightly, goes up, and finally phi m will go beyond the knee point and go towards saturation. Your transformer will fail. So the question is, for how long this can withstand DC? That depends on how long it will take for this to reach the saturation value. So it depends on the inductance of the transformer, the voltage that you are applying, and the time for which you are applying. So this is how your unidirectional excitation works in a typical forward converter. Not only that, in a typical square wave inverter. In a typical square wave inverter, if you look at a half cycle, you are applying DC. There is no AC in that. There is no change in voltage instantaneously. So you get a triangular flux in a square wave inverter. Straight line will go up and come down. Now we'll take a look at the magnetic materials that we have. We have classical core was CRNO, cold rolled non-oriented core. And then we had CRGO core, that is cold rolled grain oriented core for lesser losses. Flux density in both the cores are almost the same, but you have lesser core losses. These are restricted to mostly 50 Hertz application or 400 Hertz application. We also have something called as a laser scribed CRGO, where the CRGO material has been characteristic has been modified by scribing with a laser on the surface so that you get lesser losses. It's a different aspect altogether. It defines the total surface area into domains so that movement is made within the domain. So the physics is different. You have less loss. Then you have powdered iron cores. Why do we laminate the cores? To reduce the eddy current loss. And if you think of making it thinner and thinner, smaller pieces, then you can think of making them into powder. So iron, silicon and steel basically is made into powder and bonded with epoxy to give you specific shapes, and they are powdered iron cores. Amorphous cores, typical brand name is Med Glass 1 manufacturer, are a different type. They are amorphous, they are made out of thin ribbons, and they are stuck together to give you a particular shape. And you have nanocrystalline cores, again in thin ribbons, very thin, maybe 0.3 mm thin, and then you go to ferrite cores. These are the most of the thing. This is from the lower frequency. As you move to the higher and higher frequencies. Let's say powder iron core is good for making DC chokes, but not good for making transformers, because still here you have a distributed air gap in the powder iron core, which is very difficult for you to take into account as a transformer. But it's good as a choke because you have a distributed air gap. You find out what is the effective air gap inside it. You don't know, it's not a specific discrete air gap, okay? Amorphous cores are still will be working with at higher frequencies, and ferrite cores is the final thing. Ferrite, unfortunately, is not a metal. It's a mixture of oxides of metals, but it gives metallic characteristics, similar magnetic characteristics, and they are brittle. So they have to be molded into shapes just like our porcelain cups and dishes, and they have to be fired in the ovens to get it. So when you get it out of the oven, the shape is not 100% accurate. So have to be machined. So therefore, if you take ferrite cores, you'll find the catalog that there is a certain tolerance to every dimension. You don't get it. It has to be machined and given to you. Now ferrites have very low losses at higher frequencies, but unfortunately the flux density that you can permit in a typical ferrite core will not be more than 0.4 Weber per meter square typically, compared to about 1.5 Tesla or 1.5 Weber per meter square in a CRGO core. So you see the difference. Apparently the size becomes smaller, apparently, but no. When you take a sizing of a transformer, often in the electrical expressions we miss out the thermal aspects. It's not there in the electrical expression when you write E is equal to 4.44, etc. So what happens is, if you use a CRGO type of core at higher frequency, the losses in that core, both eddy current and the hysteresis losses, become so large that you cannot handle the loss. So what you do is, the only alternative, loss is dependent upon frequency and the flux density. Frequency is something which you can't change because that's the application. So you try to reduce the flux density. So as you reduce the flux density, the size increases for the same transformer. So now you will be able to understand, when you go up to higher frequencies, ferrite cores, even though it's only roughly about 0.4 Weber per meter square, can handle several kilohertz easily, the normal ferrites. And you get the special grade of ferrites that can operate beyond 200 kilohertz. So ferrites are the choice for the high frequency, and for the low frequency you can use any one of these. And this is for DC chokes in high frequency applications, and this is for mostly used for AC chokes in line side chokes of converters. Nanocrystalline cores, I am told there are some manufacturers in this country yet, but I'm not sure. This is made by Usha Amorphous in Delhi. Okay, so when you have this second drawing is to inform you that when you have a unidirectional excitation, your flux density may have started from the main 0 point and goes up to the top point, but when it comes back, there will be always a residual value of flux density remaining, depending on the retentivity of the material. So the next time when you start for unidirectional, it will be this, because you have only increased current H to certain value and brought it back to 0. So in that process, flux density need not always come down to 0. It depends on the width of hysteresis of this curve. So if it does not come down to 0, the next time you start is from this point. So the effective delta B variation that is permitted is B2 minus B1 and not the absolute value of B2. So in your calculation you have to be careful about this. Check out the retentivity, and if you are having a unidirectional flux operation, the deviation permitted delta B is B2 minus B1. Okay, these are some of the things I can skip. Okay, temperature effects on the core. Most of the magnetic material core you will find, I'm sorry for this drawing, I tried to do it, it was not a very good drawing, but just to illustrate the process, we'll give you graphs of the BH curve at 25 degrees centigrade, and this is what happens at typically about 100 degrees centigrade. The graph stoops down. So as a designer, I might have looked into 25 degrees centigrade curve and decided if I keep my flux density at this point, I am still within the knee point region, so my design is safe. But in real operation, when the core gets hot, becomes 100 degree, you see that flux density which I'm impressing onto it makes it go into saturation. So you have to always take the BH curve at the higher temperature while designing and not at the lower temperature. Otherwise you'll have unprecedented magnetic problem in your design, because your core is going to run hot. Whether the core itself generates heat or the coil over the core generate heats, it's the one and the same. The core is going to get hot because of either one of these two reasons. And so you have to be very careful. Okay, we have laminations basically to reduce the eddy current, and in laminated core construction, the flux is in this direction, so you have laminations like this. Okay, shell type transformers is one particular type of construction, shell type, because you have a middle limb and you have the coil inner and outer, and I don't want to mention which is primary, secondary, that depends on your application, and you have the yoke going around. Because the flux is assumed to split equally on both directions, the size of the core on either direction can be having a width which is 50% of the middle limb. Look at the core type transformers. The core type transformer, core type construction transformer or choke has the yoke going round and round throughout, and the coil is split on two sides. Now for the same design of voltage or current, the window area is going to be the same in both. this window is going to be the same in both, because this has one inner winding and one outer winding, and this has 50% plus 50%, 100% of outer, and 50 and 50, 100% of inner. So the window area is the same. If that happens, you'll find that the height is more for the coat type, because now the yoke has to carry the entire flux, whereas here the yoke had to carry 50% of the flux. But you get much better cooling, because the surface area, what you had here, first of all, it was embraced within the limbs. It was not getting 100% cooling. Now you have the same cylinder split into two 50% size cylinders. So the surface area is going to be much more, not double, it will be more than what you had. So you have much better cooling. So invariably in power applications, when we design transformers for power electronics, we select this. Shell type is only for very small power applications, quick assembly. None of us use in the industry shell type. It's all coat type. Now we come to conductors. What shall be the shape of conductor that you want? Whether it should be a round conductor or a rectangular conductor. It's not really a matter of that you can choose. It comes from, utilization, the effectiveness. I would like to use a rectangular conductor because the next conductor I place next to it, and there is very little space in between. So wastage of space is the minimum. What we call as window utilization is the maximum in rectangular conductors. If I place another round conductor next to it, there is a lot of V-shaped and V-shaped area which is lost. So I would like to have a rectangular conductor. Problem is, practically, if you have a very thin rectangular conductor, while winding, the wires will twist, and it doesn't make sense to maintain the rectangle, because this rectangle may be like this and the next one may stand up like that. So it doesn't make sense. So all the thin wires are invariably going to be round, because no matter how much you twist, the cross section remains round. So space utilization is there, and if you're thinking of bigger sizes, then only rectangular conductors are effective in implementation. In small size, it's not effective. I'd rather say below a few millimeters at least of width, we don't have rectangular conductors being useful. I mean, theoretically they can exist, but they are not useful, because by twisting on the wires while winding, you can't control it. You have different types of losses in the conductor, particularly at high frequency, also at lower frequencies. First of all, you have the skin effect. Because of the skin effect, most of the current tries to concentrate on the periphery of the conductor, and so effective utilization of the conductor is not there. So when you talk in terms of current density, amount of current per square millimeter or whatever it is, the actual current density in this part is much higher, so your effective resistance of the conductor is much higher than the DC resistance, and that we call as the AC resistance, because all the current is flowing, or rather most of the current is flowing through a part only of the skin. So you have higher AC resistance. So the solution is, you don't go in for very large diameters, because the AC resistance depends on diameter, we'll see. We also have proximity effect. Two conductors carrying currents in the same direction or opposite direction will try to change the distribution of current in the adjacent conductors. And we also have the eddy current effect. Most of the eddy current effect comes because of the flux that's coming out from one winding and trying to come out, hit the conductor from the other side. So you have an eddy current there, in the eddy current losses in the conductor. It's mostly due to leakage flux that comes in. Okay, this is the skin effect, and therefore in order to keep the skin effect as small as possible, that means trying to keep the ratio at near unity, you can't make it unity. A bundle of insulated conductors is to be used instead of a single wire, or you go in for a thin foil of conductor. Make it as a thin copper foil. The problem in making foil is you can't expect to put parallel foils for large current applications, because they will never share equally. When you have parallel conductors, either in a bent condition, the outer one has a more path length than the inner. So therefore, because it has its radius is larger, so the most of the current will try to flow through the inner, and the outer existing there but will not carry much of the current. So you lose. So what we do in bigger transformers is we transpose the wires. So you change the position of the wires, make the outer for some time come to the inner, and so on. Once you have foils, in transposing within the foils is very cumbersome and difficult for production, because you have to take a connection out and then bring it in. It becomes too cumbersome. The overall size of the winding may exceed the size of the core. So that is a big problem in using thin foils. This gives you a rough idea on skin effect. It shows that skin effect is definitely dependent on diameter. You can get this data from textbooks. And if you want to keep AC resistance by DC resistance within 5%, that is 1.05 value, you have to stick to this formula where in the denominator root F is the frequency in hertz. So that tells you what is the maximum diameter permissible for one conductor. Now you go in for multiple conductors to create the current carrying capability of the winding. Okay. This methods to reduce the skin effect is a bundle of round insulated conductors, each with diameter less than the maximum value. Then you also have the commercial Litz wire, which comprises of such wires twisted together with solderable lacquer, so that the moment you touch the soldering iron, the lacquer melts because of the heat and it permits the multiple solderings simultaneously. You don't have to remove the insulation. Or a thin foil with thickness less than the maximum value of the diameter specified can be used. Look at the insulation. After you make the winding, you have to put sufficient insulation on the winding. You might say that the wire is insulated. Yes, I agree. But when you are making a winding, there can be several cracks developed in the insulation. How do you know? Put the wire in, as an example, put the wire into a bucket of water, pass electricity from one side and see whether the water is getting electrolyzed or not. You can make out if there are bubbles coming out. So there are maybe cracks. We don't do that, but just to be on the safe side, we put additional insulation on the wires just to be sure that even if there are multiple cracks, we have it covered. So insulation will come according to certain classes depending on that maximum temperature withstand capability, as in the table. Maximum temperature withstand capability of the transformer is going to be decided by ambient, the average temperature rise of the transformer, the hotspot temperature, because I said average, there will be some point which has the highest temperature, and that highest temperature must be at least 10 degrees centigrade lower than your maximum temperature for the insulation to survive. Otherwise, the insulation does not survive. Suppose I take class F 155 and I permit the hotspot to go up to 155. In a recent failure analysis, I proved to them this is going to happen because they are not measuring taking into account the hotspot temperature. So it will fail. The hotspot will be much higher, and over a short period of time, the insulation will lose its characteristic and windings will touch together and things will become a short circuit altogether. So you have to take into account the class of insulation. Now the catch is, suppose I take an insulation of class H, 180 degrees centigrade permitted, because for many power electronics applications we have to do that, high temperature permissibility. And then the entire core is also, coil is fitted on the core, and then the entire core goes into the heat chamber for curing of the varnish. Most of these varnish will not be air drying. You have to cure them, put them in a certain temperature for certain hours. Within that, you may find that some of the coils have the magnetic components are not giving their desired performance. Why? It's not because of insulation, because of the curing temperature of the core. The temperature for curing the varnish is usually higher than that temperature, and in that process you may have damaged the core characteristics. If you take the temperature of the core beyond its curie point, it will lose its magnetic property as it had. So you have to be very cautious about the curie temperature and the temperature, and therefore the class of insulation you're using and the curing temperature. Otherwise your perfectly designed product will land up with a catastrophe. Okay, we can have in larger laminated core power transformers because we have a lot of megawatt rating designs. So we can have either rectangular core with rectangular winding or stepped core with circular winding, meaning something like this. We can either have a rectangular core with a rectangular type of winding, or we can have circular type of core which is actually stepped, because you can't make it into a perfect circle. You need infinitesimal pieces of lamination. It's not possible. You have packets of lamination with circular winding. What are the advantage and disadvantage? A rectangular core with rectangular winding gives you the adjustable width of the transformer. Suppose you tell me I have to fit the transformer within this only for a particular kVA. I can reduce the width, make it longer this way and make it fit into my equipment. But if I choose a circular core, I don't change. A radius in either side is radius. I can't change the dimension. I can't make it fit there unless I have to reduce the size. So fitting sometimes becomes the important factor in equipment. So therefore, most of the equipment type transformers are made rectangular cores, but if it is not given that restriction, then we'll try to go in for a circular core, stepped core with circular winding. Why? Because the mean length of one turn in circular winding is always lesser than what you do for a rectangle of the same cross-sectional area. You can just work out for yourself. You take the same area of one circle and the same area of a square and try to find out the perimeter length. You will find the minimum perimeter will be for a circle. So we have less copper. Less copper means less losses, less temperature generation. Everything is beneficial. Okay, these are some of the transformer constructions that we have. We have transformer construction like EI, as I said, shell type. These are only for low power transformers, not at all used for big power transformers. Then we have toroidal constructions. Many of the manufacturers are going in for toroidal constructions because cooling is very, very good all around. You have a cooling surface all around, but you have to be very careful. All toroidal core constructions are prone to high inrush currents. Inherent construction does not have any air gap anywhere along the path length. So when you push it, when you make your switch on, it can go through a huge inrush current and there's hardly anything limiting. Why doesn't it happen in this? Because of the small gap here, maybe fraction of a millimeter air gap at the joint, that limits the inrush current because the reluctance of air is quite large there. You have a joint, so the joint is also helpful in limiting inrush current. Any variac that you use in the lab, circular construction, you will have an inrush current. You will have a breaker tripping or the fuses blowing out initially. That's nothing to do with the good performance or bad performance. Is because of the toroidal construction. Here you don't have a joint. It's a continuous strip. You also have certain wound core type of things in specialized applications where the core is wound in strips and then the bobbins are split. Bobbin is fitted onto the core, fitted to the machine, then the bobbins rotate and then the wire is wound onto it. You have scrapless EI stampings. I'll just quickly go through. These are only small applications. You have particular ratio so that they are scrapless. So what happens is you have one E, a second E and one I and another I punched out together without generating any loss. That's why they are called as scrapless. In order to do that, you have a simple expression. Their relationships will become fixed. So this is for a shell type. You can have a scrapless UI stamping also. These are used several times. Okay. We may make a transformer, small transformer out of CRGO stampings, but the orientations will be something that you can see here because of the lines. I has come from this part. Now, we know if it is out of CRGO, we think that if I make this out of CRGO, the core losses will be less compared to CRNO. It may not be so, because you have the flux path and you have additional losses at this point where the flux is entering perpendicular to the direction of orientation. So you will have additional losses at these points. So ultimately you will find that the difference in efficiency is negligible. So many of the transformers, EI transformers today are not made out of CRGO. It's made out of still CRNO. You don't get any benefit in this type of construction. Other constructions, yes, you will get benefit. Now, so at the joints, what we have to do, we have something called as a separate method of making joints, so that this is one of the, these two are one of the better joints where you see it's along the, along the orientation and then changes at ideally 90 degrees along the next orientation and then changes. So there is no flow of flux across the orientation. Okay, this I can skip because it just shows that the sizing of a transformer is decided by the area product, which is actually the product of the area of the core multiplied by the area of the window, and that you can express in terms of the VA or rating of the transformer and certain characteristics. This is the primary VA rating, VA rating of the primary of the transformer. This is the VA rating of the secondary of the transformer. 4.44 is for sine wave, F for frequency, maximum flux density, this window utilization factor, and current density. Primary and secondary VA need not be the same in any application. It need not be, it depends, because that's not the way VA is defined. The power transferred from primary to secondary may be same, but the VA rating of a transformer is decided by the RMS amperes and the RMS volts rating of each winding. Whether you are able to load it to the full extent or not decides its utilization. I'll give you an example. Okay, this is another form of the same expression. You can express it in terms of the average kVA with an empirical constant. Okay. Take a look at this. This is a class 12 rectifier circuit. The it's a full wave rectifier. You have a primary sine wave and you have a secondary half sine wave, and I've used a resistive load, so the currents will also be half sine waves. Here the load current is going to be a rectified sine wave like that. Fine. So what is the current flowing through this? That RMS value is for this with a 0 component here, peak by 2, not peak by root 2. Peak by root 2 is for this or this. This will be peak by 2. So it becomes root 2 peak itself for the sine wave is root 2 times the RMS value. So it becomes RMS value by 1.414, IS by 1.414, and have assumed a 1:1 turns ratio. So total V on the secondary because of the other half is 2 times of that. So you can find it's root 2 times VS into IS. On the primary side is VS into IS. So secondary VA rating is root 2 times. So avoid using this type of transformer because the size of the transformer is going to be big. Why? Because this winding is there, but is being utilized only for half cycle and not utilized for the full cycle. This winding is also there, is being utilized for half cycle, and this lying and occupying space means the size of the transformer is being increased unnecessarily, but you're not able to utilize it. So therefore, even full wave rectifiers or push-pull circuits have all this similar type of disadvantage. Go in for a full bridge. Okay, we talk about leakage inductance. Minimum leakage inductance definitely gives the minimum voltage drop. It generates minimum voltage stress on power semiconductors and achieved by very close coupling between the windings. And sometimes leakage inductance is required. For example, if you study diode rectifiers or thyristor rectifiers, you'll find that commutation overlap is there. So if you have a transformer right at the input side and you have a certain amount of built-in leakage inductance, commutation overlap does not distort your power supply voltage to a large extent, because during the overlap you have a practical short duration short circuit of the supply, and the inductance in series is going to support the voltage for that time, so you don't get deep notches. Thyristor rectifiers are almost out from normal applications, but they are going to come in once again with hydrogen rectifiers. All the submarine battery chargers that we make, megawatts, are all thyristor because they are rugged. Everybody wants rugged equipment. Yes, efficiency wise they are not really bad. Most of the efficiency there goes because of the transformer and the chokes. But they are rugged. They gives us less than 5% THD on the input side because we have 24 pulse rectifiers, and that's more suitable for such large power applications. And minimum leakage inductance is achieved through minimum turns, higher length of winding, something you must note if you want to reduce the leakage inductance. This is the formula for leakage inductance taken from any textbook. If you look at the formula here, leakage inductance, you'll find the height of the winding is at the denominator. So if you make the height bigger, your leakage inductance for the same number of turns, same core area will come down. And if you have more number of turns here, less number of turns, then also your leakage inductance will come down. So if you want to make a transformer with low leakage inductance, change the type of core to get such benefits. It's not necessary that the core that you are using has to be the best. If you can't do it, interleave the windings. That means, for example, you have a primary and a secondary. You split one which has the largest number of turns into two, sandwich, that means 50% of that one, the higher turns is wound first, then 100% of the lower turns, and then again balance 50% of the higher turns, join the two higher turns in series, and you get lower leakage inductance because you are interleaving in between. More than once interleaving theoretically gives you better performance, but not significant. It decays down, the performance decays, and complications increase as you go on making interleavings. Okay, we come to inductors. You're all aware of inductors, and we use an air gap in between. Why do we use an air gap in between? I can make an inductor without an air gap just by core. The fact is that if you want the reproducibility of the inductor, then it should not depend on the characteristic of the material alone, because today the material that you get with the particular mu r, you may not get the same mu r tomorrow, but your inductance design must hold true. So you put an air gap in between there so that most of the reluctance is decided by air rather than the material, so that if the air reluctance dominates, then even if there is a small change or a large change in the characteristic of mu r of the material, your inductance is going to be more or less the same. That's one of the major reasons why we put air gaps in the inductance. Now, moment you put an air gap in the inductance, you have something called as a fringing. The flux should have, all the flux should have gone down. This is not leakage, this is fringing. Leakage happens between two coils which are to be coupled together. This is happening in the core. And the flux, instead of going down, tries to come out of the air, follows a higher reluctance path and comes back to the core. That's fringing. So because of fringing, the effective cross-section of this part of the flux increases. So you have an effective increase in the area of the flux at that point. So if you are trying to calculate the total reluctance of air, if you take only this, you will be wrong. You have to take the larger area here. That is a bit complex, so you have to see later on. Now all the inductance again, they at high frequency, they are not going to behave ideal. So you have a resistance, you have an inductance, a shunt resistance, and a capacitance. This is your pure inductance. This is your loss component. You have a core, so you have a core loss. In air gap, air core resistance, you don't have inductance, you don't have this. And this is the resistance of the wire which you have used to wind. And this is the end-to-end bulk capacitance that I have represented. It is actually a distributed capacitance. Why distributed? Because when you make an inductance, you have number of turns. So each turn to turn adjacent has a different potential because the inductance drops a voltage across 10 turns. So each turn to turn is total drop by 10. So you have insulation in between, so it forms a capacitance. Very simple theory. So because of that, I've taken a lump representation to show what it is across, and that's what you have. So at high frequencies, you may have severe problems. Your current may be flowing through the inductance. It's not blocking the high frequency current because the inductance is there, but the capacitance across the two ends may be significant at that frequency. As I said earlier, a small capacitance is not the question. The reactance at the frequency is the question. If the reactance becomes comparable, then it's going to bypass. When you have two parallel conductors or two resistances, if one is a 1 megohm and the other is a 20 megohm, still you understand that most of the current will flow through 1 megohm. It's not the absolute value, it's the relative value that matters. Okay, these are some of the high frequency inductors that are used. Different shapes. Okay, here you can see a banding put around the air gap. That is a Faraday shield, so that most of the stray flux from fringing cannot come out and create interference on the others. But the moment you put a Faraday shield, it's outside the windings and it is a short-circuited winding outside because you're not supposed to have any active flux outside. But moment you put that, remember there will be a certain amount of loss in that foil. Because of the flux that gets coupled to it, it circulates and there is a little loss in that. This is a toroidal type of choke construction, but there is no air gap visible. Because this is not ferrite, this is a powder iron core. It has a distributed air gap. It might look the same. How do you distinguish between a ferrite and a powder iron? Take a little hacksaw blade and try to cut. If you can cut through, then it's iron. If you saw slips, it's ferrite. Okay, here you can see segmented bobbins which are used for these chokes, because to limit or restrict the interwinding capacitances. So you fill up this segment first and then go to the next segment and then go to the next segment and so on, instead of having a continuous winding. So interwinding capacitance becomes reduced in such type of constructions. Okay, this is about the fringing effect. I don't have to go into details of it. These are some expressions for the inductance design. And similarly, like in transformers, you can define an area product for the sizing of the inductance. This is fringing. It's very simple formula, but in most of the cases, you will find that this does not work. This works only for small size chokes. It does not work for bigger size chokes. Okay, when you have laminated inductors created, as I had shown earlier, lamination, and this is the direction of flux. But take a look at this figure now. Suppose this is an air gap here. Much of the flux fringing is coming out 90 degrees to the surface, which means the flux is coming out in this direction. And you do not have any lamination on that direction, so it will form an eddy current on that direction. If that happens, you have high losses in this local area, and the temperature near the air gap around this point can become very, very large for the core, and it can lead to damage of the insulation of the winding. And that heat is not generated by the coil. That is generated because the fringing of the flux is coming out at 90 degrees, and you don't have a lamination for that. You have a lamination for the main flux. It will not happen in ferrite cores. It will only happen in cores that are laminated to reduce eddy currents. It will happen in your CRGO type of cores. It will happen in your amorphous cores. So what is the way? You keep your winding away from the edge. Don't keep the winding close to the edge. Keep it away. Then you will be safe. If your winding is up to the edge, the insulation will get damaged because of the high temperature. Metal clamps next to the chokes create a lot of problems, because you can understand now, much of the flux, fringing flux, will try to get coupled with the metal clamps. So if you're creating an inductor in your lab, don't try to clamp it with metal clamps. If you want to clamp it with metal clamps, ensure that there is a clearance distance in between. How do you do it? Put an insulation there. Some thick insulation, insulating material, non-magnetic, put it there and then put the clamp. So the metal clamp is little far away from this, so less flux will be there, so less losses will be there. And this will become hot. You can check it out, just put it adjacent, and it will be hot only at this air gap point, because the fringing flux is going to create eddy current loss in that. Okay, now I think I can skip this basic thing about power semiconductors. And we have diodes as we use, and diodes are subjected to reverse recovery effects. You have a large voltage shoot because of the reverse recovery effect. A diode does not have a reverse recovery effect if it is started for the first time. But if a diode was conducting a current already, and now you are applying a reverse voltage across it, because of the reverse voltage application, the carriers have not yet got time to get recombined or removed, and it permits the reverse conduction. When that reverse conduction tries to clear itself out because of the reverse bias, then you have di by dt created here. This di by dt is a positive di by dt. And if there is a stray inductance in series with the circuit, you get a large dv by dt created because of that di by dt. So we categorize diodes into by recovery time, rectifier diodes, fast recovery diodes, and ultra fast recovery diodes, or by recovery characteristics, hard recovery and soft recovery. Hard recovery means that this will be very rapid. So you have a large di by dt, you have a higher voltage. And soft recovery means this will be relatively slower. It does not mean that TRR will be large for soft recovery. It's a relative ratio that's important, not the absolute value. And of course, we have Schottky diodes. Schottky diodes have no really reverse recovery effects, so they are one of the fastest, but very expensive, and you don't get it in high voltage. Okay, I think I can skip some of. Okay, one more point that I wanted to say here in diodes. Once you try to select a diode, don't be tempted to select a diode for the highest voltage. As an example, in your circuit, you're working with 100 volts. Maybe you need 150 volts diodes, but you have a 1 kilovolt diode and you think that's going to be safe enough for your circuit. Yes, it's safe, but every high voltage, the higher the voltage for the diode, the higher will be the recovery time. So it will become slow, it will become sluggish, because the total layer thickness has to be large for blocking the voltage, so your recovery effect will be slow. Don't unnecessarily go in for a very high voltage rating diode. Try to be close, select to be close for the fastest response. Power MOSFETs again, okay, you have a diode inbuilt because of the parasitic bipolar transistor that's inside it, but there's no guarantee that the diode is going to be fast recovery or ultra fast recovery here unless you check the recovery time of the particular device. And simply by putting a diode across it reverse does not imply that that diode will conduct, because it depends on the relative drop between the two. So the one with the lowest drop will conduct first. So you have to check. Just arbitrarily putting a diode in parallel does not imply that it will conduct. Okay. IGBT is similar. You have a parasitic bipolar two bipolar transistors, so it creates a parasitic S here. Although modern technology today has reduced the effect of the parasitic to a drastic extent, but still it is there, and there are chances that at high dV by dt across the IGBT may latch up, in which case you will lose control. High means more than about 3 kilovolts or 4 kilovolts per microseconds, then you can have a problem. Less than that, you don't have a problem. Many of you will be aware of this concepts of power loss. We have a voltage switching, and so we have a voltage. This is the on time, so voltage comes down. This is the turn on time, and this is the turn off time. So switch is switched at this instant, but it has taken time for the voltage to come down. As long as there is a current conduction, the voltage remains low, and when you turn it off, it goes up, and so the current comes down. And as you plot the instantaneous power dissipation in the switch, you will find there is a small amount of power dissipation here, but a large peak at this point, because the simultaneous existence of voltage into current is quite large here. So you have a large peak. Now the turn on time of a device is defined by the time taken for the voltage to come down, not by current. Okay? And the turn off is decided by the time taken for the current to come down and not by voltage. Because you don't take the current rise time, because that can be delayed by parasitic elements in your circuit like a strain inductance. It can delay the rise of current, but the rise of voltage will be defining your on time. And here turn off is decided by current, not the voltage, because you may have a snubber across the device which will make the voltage rise slow. Nevertheless, when you plot the average power, it is low at lower frequencies. When I want to go to higher frequencies, it means I'm just trying to push them together, closer to each other. So I'm trying to reduce this time. But I am not altering this time at all. The device time is not getting altered. That's a characteristic of the device. So when I go to the higher frequency, you'll find that the average power loss goes up, because the contribution of this is much more. I have brought them together, so the area remains the same almost, and the average value simply rises up. So there is a high switching loss for every device that you take, and so that decides the upper switching frequency that you can manage. There is nothing called as an absolute upper switching frequency. If you can manage the heat, it's fine, you can switch it at that point, plus efficiency consideration. Whether the efficiency what you get is within your acceptable limits. What happens at high voltage for a device? For a diode or any other semiconductor device, you have a particular maximum breakdown voltage. With temperature, the breakdown voltage falls. So if the junction temperature is going to go to a higher temperature, the effective breakdown voltage of the device gets reduced and it just collapses. For example, if this was 200 volts and I was operating with 100 volts in my circuit, 200 volts is safe enough. But suddenly at high temperature crossing Tmax, this drops down below 100 volts. So obviously it will start conducting. And then once it starts conducting uncontrolled fashion, then many things will happen, lead to damage within the device because of power dissipation within the device. So always be careful of the temperature, and that's the reason you have to make thermal managements. Paralleling of devices, MOSFETs are easy to parallel because of the inherent positive temperature coefficient of on-state resistances. easy paralleling of IGBTs that have positive temperature coefficient. All IGBTs do not have positive temperature coefficient. If they are having positive temperature, you can parallel. But paralleling again brings in a second factor, that whether the pulses are going to reach the two devices at the same time or not. So that is another challenge from the driver side, more for the higher frequency applications. And diodes from the same batch of production can be parallel because we assume that they are closely matched. Okay, drivers, you can have non-isolated drive scheme, you can have pulse transformer isolation, you can have optical isolation, you can have floating drivers. Pulse transformer is sometimes convenient because you don't need a power supply on the secondary side. Optical isolation, you need a separate power supply on the secondary side. So it depends on the size, the economics of the product, where you will make a judicious decision. I'm not going through the details of these. Okay, snubbers and clamps. Snubbers are used in diodes to control the voltage spikes due to reverse recovery effects. There is no concept of dV by dt in a diode. In SCRs, the snubbers are used both to control the reverse recovery effect and to limit the dV by dt across the SCR. Because diode, once it is forward biased, it will turn on. It is not going to block at all in the forward direction. Snubbers used in switching devices to control turn-off losses. And of course, clamps are used to limit voltage spikes across semiconductor devices. You have a stray inductance in the circuit. So you had a switch which was conducting, and you open the switch. The trapped energy in the inductance will try to maintain the current flowing. So it will create a spike positive on the right hand side in my drawing, which adds to the supply and creates a large voltage here. So across the switch, you get E plus L di by dt. So that is your problem. So maybe you can put snubbers and clamps to take care of that. Snubbers mostly control the rate of rise of voltage across the device, and snubbers are always fully discharged. The capacitors are fully discharged. Clamps, on the other hand, behave more like a Zener diode, and most of the time the clamps are not fully discharged. They maintain the voltage across the capacitor. Only if the voltage across the switch exceeds the capacitor voltage, then it absorbs the energy. Clamps and snubbers can be non-dissipative also. That means the energy can be sent back into the circuit elsewhere. Now, instead of putting snubbers and clamps, the best technique, of course, is to reduce your stray inductance. That is the root cause. It's like you have a fire and then you have a fire siren going on. No point in trying to shut off the siren, rather put off the fire, access it at the source. So if you are able to reduce the stray inductance, you may not require any snubber or clamps. That should be the aspect of your design, because you have a lot of energy loss in that process. These are some of the examples of snubbers and clamps that we taken in a buck converter and flyback. So snubber is in the blue and the clamp is in the red. They do their own function at the specific points. Okay, I can skip this. Protection. Proper handling is to be made for preventing damage due to static charge. MOSFETs, you just can't put it in your hand or rub it. You have static charge generated on your skin, on your clothes, and that can damage the gate of oxide layer before you ever energize the MOSFET, because that oxide layer at the most can take roughly 25 volts of voltage. Beyond that, approximately 25, some have 30, 35 ratings. It just gets damaged without ever energizing the MOSFET. Only diodes and SCRs can be protected by fuse, because you can define a I square T rating, which is basically the sort of a power rating for the devices, because their voltage drop is more or less constant. You can define some power rating. You can't do that for the control device, because the voltage drop depends upon the drive that you are putting in. So you don't have a fixed I square T for the other device, so it's not possible to coordinate a fuse with them. You can coordinate a fuse with the bonding wires inside, but not with the devices. Okay, shutdown is required to protect MOSFETs and IGBTs from overcurrent. Snubbers are recommended for IGBTs and high voltage applications. To limit, proper heat management is required. Okay, we can skip these. I think I can skip the part of soft charging of the DC bus capacitors, because we have something more important to deal with. Yeah, okay. Interference problem. Electromagnetic interference, and the old terminology was RFI, radio frequency interference. That's something like a mystic area. mainly because you don't see it, the network. It is there. You have to conceive it in your brain. It's something like in a dark room. You just can't see it. Okay. So electromagnetic compatibility means your system must be compatible to external electromagnetic interference and should keep performing its operation. Noise is a general terminology. Interference is a general terminology. Susceptibility, also known as electromagnetic vulnerability, and regulatory standards are there. So we have different types of standards. You have test systems here in Bangalore also. I mean, 1 month back I was here for testing one equipment in one cosmic lab in the electronic city. You have good facilities here. Generation of noise in converter circuits. Why do they generate and how do they generate? Switching currents by semiconductor circuits, particularly if you have an inductance coupled. So if you interrupt the current, the high voltage created LDI by dt generates an interference, magnetic interference. Large dV by dt, reverse recovery effects in diodes, stray magnetic fields from transformers and inductors. They can all create interference on this power electronic circuit. You can have a conducted noise to the back to the input. So if your system is generating noise, it will create a noise backwards. Noise is anything that is unwanted. You can have a noise going to the output side, and you can have a radiated noise which will be picked up elsewhere without being conducted. How do we have these noise couplings? One is conductive coupling. You have a direct conduction. This, and also you can have a coupling through common impedance. This is an example of coupling through common impedance. You have a slightly higher resistive path for the return path. Circuit 2 is going to have a change in its current. So it creates changing current I2, creates a changing voltage here. So that is going to affect the voltage that's there in circuit 1. So you have a change in the supply here. You have capacitive couplings, like here. You think that the two systems are isolated from each other, but there is a certain amount of capacitance between them because they are displaced in air. Air forms a dielectric. Capacitance may be very, very small, but you can still have some coupling, and therefore you can have a capacitive coupling between these two boxes placed on the table. And with respect to earth, our reference is always the earth for all the interference situations. We define the noise into two types. One is a differential mode noise, which comes as a difference between the two wires that are supplying. So the model is, this is the supply source, here considered AC, along with a series noise source. Or you can have a common mode noise, which comes with reference to a common platform through any one of the lines. Maybe it is the AC source coming across the live or through the neutral, and the return path in the common case is the earth, the mother earth. It returns to that. Now question may be, I have equipment on the table and is very well insulated from the floor, then how does the current flow through the mother earth? The question is, it's not resistive, it's capacitive coupling there once again. So you may have a small capacitive coupling there, and the current flows. This is a high frequency current that will flows through the capacitance, and that's how things return back to neutral. And more particularly, because the supply side AC supply, one terminal, the neutral, is always earthed at the substation. So that completes the path back to the supply substation. So if you can ask me that, okay sir, if I have a floating supply, will there be common mode noise? It will be drastically reduced, definitely. For example, if you operate with a battery on the table, you will hardly have any common mode noise. The moment you operate with the power supplies from the mains, you are bound to have more and more common mode noise. These are top sources how common mode is coupled. There is a dotted line showing the outer box of the equipment, and this potential is changing. It's once going to ground reference and going up. So you have a changing potential. There is a stray capacitive coupling. That's what I said. You can't see it, but it is there. It's a network of capacitance. So potential is changing. This potential can change, this can change. You have capacitance between the windings because the two windings are separated by dielectric, and so on. The catch is, in a network of capacitances, if everything is steady, all the voltages are steady. If you change one voltage, then the network is disturbed and the current will flow through some of the elements to trying to restore another stable point. So that is where the noise spreads to the other side of the system, because you are disturbing the network through some mechanisms. Heat sinks, even though it is insulated, you still have a capacitive coupling. The from the device, because the device potential can change. You can have stray flux coming out of your magnetic components. Your transformer, for example, you have parasitic capacitances in your transformer. I'll give you a simple experiment. 230 volts to 6 volts, any transformer you take, connect the oscilloscope on the outer output side, switch it on. You will see almost 230 volts appearing instantaneously. Why does it appear? Because it was not supposed to go by turns ratio. It has happened because of these capacitances. They were at zero potential initially. So if you switch it on, they remain at zero potential initially. So they act as short circuits initially. So zero voltage means they will transmit the 230 at the output. How to go about it? You put a small capacitance on the output side, maybe a 0.5 microfarad on the output side, and switch it on. You will find now it doesn't go to 230. Why? Because you have a series network of a small capacitance, a large capacitance, and the small capacitance. And remember, the smallest capacitance in a chain drops the largest voltage. So you have the smallest voltage appearing across the output. The higher voltage has been dropped across the smaller capacitors. So that's the way you can avoid it. You can understand that it's there. You can't see it. Reducing interference, use twisted wires or closely placed busbar pairs. They have to be very close to each other so that flux coupling is there. Reduce physical distance between the switching element and the nearest capacitor coming across the lines. Let's say you have a rectifier, you have an inverter, in between you have a DC bus, you have filter capacitors. Question is, where do you place it? Near the rectifier or near the inverter? If they are far away. Best is, of course, to make them close to each other, but it's not possible all the time. So in that case, you have to split. Part of the bank will be on this side for the rectifier to cater to the ripples coming from the mains. Part of the bank will be on this side to cater to the ripples that are coming from the inverter. Use suitable shielding for radiated noise. Use large ground areas on the PCBs. Multi-layer, you get that advantage. Use appropriate types of capacitors. Use shields in magnetic components with appropriate placement of windings. Use appropriate layout of components. This is just an example that I have taken from the published data showing you how twisting helps. So you have a straight pair of conductors between two elements, and there is a stray field shown by the blue lines coming in. Here you see it's totally coupled, as if this is a loop and you have a flux going right through. It's totally coupled. If you twist it, you will see that the couplings are broken up and the end result becomes zero. For the green conductor, once it's coupled on one side and here is the other direction, so the effect gets cancelled out. Similarly, if you look at this figure, you will see that two conductors, now the field is not coming from the middle, the field is coming from one particular side, and it may be inducing roughly 1 millivolts in each of these hypothetical sections and 0.5 millivolts in the other conductor because it's far away from that side. Once you twist it, you'll see the same conductor has 1 millivolt and 0.5, 1.5. So on the average, both will have same. Its effect is cancelled out. So twisting helps tremendously. Watch the polarities also, okay? So you'll see minus plus gets added to minus plus and goes on. So the effect is the same. So differential voltage will be ideally zero. We have transformers with shields. You can put a capacitive shield in between. The effect is because of the capacitance, it will make a bypass. But putting a shield in between primary and secondary also increases leakage inductance between the two. That you have to be careful. What is your desire? Okay. Okay. Filters, you can have filters for reducing the conducted noise. This is a particular differential mode filter to take care of noise that's going right from maybe from the live line, gets a pass through the earth, and if it is coming from the neutral line, gets a pass through the earth. And this is a, and this is a common mode filter. That means if this is, the earlier one was for, this is a common mode filter now, L, and C. With respect to the earth, I made a mistake here. This was a differential mode. So you had a current, noise current that would flow right through. That would be blocked. Or if it is coming from the other side also. But here it is a common mode filter. So it has to come with respect to earth. So the noise, if it is coming, with respect to earth. Here it goes through Cy, and here it goes to the other Cy, and Cx is there. You can integrate the common mode filter and the differential mode filter into a common structure. Don't think that this is the common mode filter. This is a particular integrated magnetic structure. Most of the large power applications, we have discrete differential mode and common mode filters. In this case, the advantage is, if you use this type of structure, note that the ampere turns created by this is cancelled by the ampere turns created by this. Here the current is entering the dot, and here current is flowing out of the dot. So what happens is, the core does not see the main load ampere turns. That flux is cancelled. So your core size is reduced. Okay? Now once your core size is reduced, you are still using it for common mode, because if there is a flux in the current in this line which is not returning back through here, that flux will find a large impedance here. Something which is going here and not returning back will not be cancelled and will find a large inductance. Same thing here. Then where is my differential mode inductance? If it's only common, the leakage inductance between these two provides you with the differential mode filter, and you can also have small amounts of differential mode filter. So this is just an integrated magnetic structure. Better to have them separately. Okay, that is X and Y capacitors. Okay, this is EMI problems due to the layout. I still have a little time. Okay, yeah. This is a very bad example of a bad equipment design. So here my AC mains comes in. I have put a EMI filter here, put it to a rectifier, DC bus, a switching circuit goes out. I have put a filter, so I presume that all the interference created here is not going to go out to the lines. But the catch is this wear inside. So all the switching circuit radiated it gets picked up here and gets conducted into the AC main. So when you have a testing, you'll find all the interferences are here. The filter should not be there. The filter should be here physically at the entry point of the AC mains. Then whatever wear you have inside, whatever it picks up cannot send it back to the mains. So your system will not be sending anything output on the input side. Similarly, you can have filters on the output side also. Here you have an example of conducted noise on a PCB. You have a particular IC here, and the tracks have all inductance and resistances. I have a relay which is going to switch, so there will be a large current switching on off. Because of the large current switching, there will be potential change in this part of the circuit, so the voltage supply to this circuit is going to see a fluctuation. So how do you take care of it? Cut it here, take that, straight join it here, cut it here, take and join it here. So the high current fluctuations are not going to cause interference, conducted interference into your low voltage circuits, low power circuits. Track layout has to be very, very, done judiciously. You may have more than one trial to execute the system. Stray inductance problem for large systems, we go in for sandwich bus bars. Suppose we make 200 kilowatt inverters, we go in for sandwich bus bar system. It's a replica of a PCB. We have an insulating dielectric in between, usually fiberglass. Then we have a copper sheet on the top, and we have a copper sheet at the bottom. So it's a total sandwich system, and then you fit your components from the bottom side. Fitting the component is not going to be easy, so you have to do a lot of engineering, because this component, whatever it is, has to get connected to the lower bus, so you have a lower lead length. This is going to get connected to the top bus, so it has a higher lead length. Components don't come always with different lead length. So you have to make holes here, and this may be connected by screw. This you have an elongated connection with a hole at the bottom, so you have a connection here. So that is a different art of engineering. Main advantage is, because of this parallel plates, you have low inductance because the current is going in this direction and coming back, so the flux is getting partially cancelled, and you have good capacitance distributed inherently to the busbar system. So these are the only solutions for large power applications. It's basically, as I said, it's a replica of your printed circuit board system. And when you are measuring the noise, you have to be very careful. you cannot use your normal oscilloscope probe for measuring the noise, because the long loop of the ground wire will give you stray pickup, which is not there actually. You will see something which is not there. So what you have to do is, you have to reduce the length of this ground wire. When you remove the tip of the probe, you will see there is a small metal ring there. You make connections to that. These type of adapters are available from the manufacturers, called as bayonet adapters. Or you make your own jig by connecting a short wire around that, and then you measure at the two ends, so that the ground wire has the shortest length. Then what you see is the real ripple there, not the other ripple that you see with the long ground wire. In all these examples you will see this is a little risky, where we are trying to make one connection to the this metal barrel here and the probe tip. This is a bit risky, but you can do it if you are safe. Otherwise, you have this arrangement made with a piece of copper wire, and then you can measure the actual ripple which is there. Otherwise, you get a lot of pickup. Some things that you see there are not there, actually not there. For example, if you see spikes in your current probe, most of them are not there, because a rapid change of current cannot exist. It defies the laws of inductive circuits. You can't have a rapid change of current spike. It is most probably a pickup that you are seeing. So if you are able to observe it carefully, you will see that it is not there. If you have a Hall effect sensor based probe, most of the time it senses the external flux and picks up. So one way to do it is install a very low resistance somewhere, put your oscilloscope probe like this, measure the voltage, convert it into current. You will see spikes are not there. Okay, I think I have come to the end. Okay, this is something very common, most of you will know, and that is the process of heat dissipation. We have air natural cooling, we have forced air cooling, we have oil cooling system, we have water cooled system, where water is circulated through all the heat sinks to cool the equipment, including capacitors, and we have refrigeration based cooling. So I've come to the end. I have skipped some of the slides to stick to my schedule. Thank you. If you have any questions, you can ask me. I don't know how much it was informative, but anyway, that's what they wanted. Second thing is, many people who are not working with hands-on will not be able to appreciate what is going on, because with your MATLAB simulation and other PCM simulation, there's no stray inductance there. You have to put it in. Somebody tells me, no sir, I have used a real source. I said, your source does not have any inductance in it. It's an ideal source. You put an inductance and then see. Yes, please, somebody wanted to ask something. No, not really. No. Powdered core are used for DC choke applications or even low frequency choke applications, not for transformers, because there is a distributed air gap inside the core. Transformers should not have any air gap, because its no load current will increase. So they are not good for transformers. They are good for chokes. Oh yeah, yes. That is because of the fringing flux comes around out of the air gap, that fringing, so that flux can interfere with the external components around. To prevent that, if you put a short-circuited foil around it, that is called as a Faraday shield, so the eddy currents will be induced in that copper foil, which will try to oppose the cause. So the cause that was creating was the alternating field that was coming out, so that will get suppressed. See, you have shielding, magnetic shielding. If you want to do magnetic shielding at low frequency, you have to take a magnetic material, like say MS or iron, like that. If you want to do magnetic shielding at high frequency, your MS or iron will not work. You have to take either copper or aluminium. Then the effect is because of eddy current. At high frequency, eddy currents are induced in the shield, so they will flow, try to oppose and try to reduce that flux that was going out.
Online audience have some questions.
Yeah, please, that's up to you, how you tackle that, yes.
Please, one thing, sir, regarding the picture that you showed, that that measurement.
Measurement, yes.
High frequency
Yes.
signals. So that comes only in these passive probes. So
Mhm.
if I want to see multiple signals together, how do you do
No,
that?
each probe you have to put that. The other probes don't. You have a common ground.
Yes.
You can't do it. You can't measure the high frequency effects with that. No, that is good for low frequency applications, not the high frequency spikes. And your probes must always be matched with your oscilloscope. There's a question of impedance matching. Otherwise, your signal will get attenuated. You just can't use any probe to any oscilloscope. They must be matched in terms of mega ohms and in terms of picofarads. Because you're dealing with high frequency. Low frequency, it doesn't matter.
Sir, when you showed that electrolytic capacitor, you showed a black mark.
Oh, no, that is the polyester capacitor. I showed a black mark, yes.
Okay, so that something you told related to EMI.
Yes, that is the outer foil. When you have two foils wound together, you have a finally outer foil existing. So if the outer foil is connected to a potential that's going to change rapidly, then it acts like an antenna and spreads the radiation all around. Okay, so we don't want the outer foil to get connected to a rapidly changing voltage. Rather, we want the outer foil to be at a constant potential. That's why that marking is given on the capacitor, which is the outer foil, so that you connect your your control ground to that point, not the active part. So that way your self-generated radiation within your circuit is going to be the minimum.
Capacitor terminal, like the one terminal, the
Marking is there for only one terminal. That is the outer foil. That is just to give you an indication that is the foil which you better connect to the control ground and not to the active part. Yes, please.
In the last slide that you showed reduced pickup in that capacitor,
Yes.
you showed that the ripples will reduce. Means actual ripples are less than what you
Most of the time what you see are not the actual situation. Most of the time.
But I think it is counterintuitive as the loop is larger, inductance would be larger.
Oh, no, not that way. It acts like an antenna and has a pickup. The larger ground loop acts as an antenna and has pickup. You just try that extra loop. If you just wrap it across the probe, keep the length same, wrap it across the probe and check, your interference pickup will get reduced. It's the loop between the antenna, the probe and the wear. That large loop will pick up the signals. So if you bring them close, pickup will be less.
Pickup is like radiated noise.
Yes, actually, even in this room, for example, all of us are having electrical signal pickup. Where? From the electrical wiring around us. 50 hertz wiring is there. So, as when you turn on an oscilloscope and just touch with your finger the input point, you will see a beautiful sine wave on the oscilloscope. Check its frequency, it will be 50 hertz. Because that's all coming from the wiring around us. We are picking it up on our skin. Very low power. But the oscilloscope impedance is more than 1 mega ohm. So it gets a signal there. So it's sufficient to prove that we are picking up signals. So the probe will also pick up signals.
Proceed to one or two questions.
Yeah, so one of them
Like
has
an idea
asked,
which-
someone has asked that leakage, you said leakage inductance is sometimes useful.
Yes.
You're asking where it can be used.
Thyristor converters particularly, because we need inductance in series. So no thyristor converter can be connected to the supply lines directly. If you do that, you get large notches on the supply line and your voltage is going to get distorted tremendously because of the notches. So what we do is either put inductors in series. Instead of that, if you have a transformer for stepping down the voltage as it is, you might as well have some amount of desired leakage inductance in the transformer so that you don't need a separate inductance. That leakage inductance in the transformer does the job because in the equivalent circuit it comes in series. We typically design for at least 4 to 6% leakage inductance in a rectifier transformer.
Okay, the second question is asked by Rajarshi, but the question is not very clear to me. Regarding switching losses, in certain cases ZVS and ZCS can be implemented to minimize switching losses.
Yes, definitely. Definitely. That current and voltage overlap that I showed there, it does not practically, I won't say does not happen, but it gets reduced drastically. So the peak values come down. So switching losses will get reduced when you have ZVS or ZCS switching, definitely.
Okay, the Bharat is asking a question. High frequency transformers are used for isolated DC-DC converter, but is there any particular value beyond which we should go for isolation, such as leakage currents or anything related to power side?
No, isolation is decided by something entirely different. First of all, it's decided by human interaction, whether I need isolation or not, number one. Number two, common mode currents, whether common mode currents are going to flow, and isolation is one common, very simple method of breaking the chain. You don't have a common mode currents. Third, maybe a voltage scale up or scale down. So I cannot give a unified solution to it. It depends on the application, whether you have isolation or not. But there's no limit. You can go up to fairly large application. I myself have designed and implemented up to about 35 kilowatt of power in high frequency application ferrite transformers. But of course you don't get a single core. We stack the cores. Single core is not there. We stack the cores side by side to increase the total ampere, capacity of the transformer.
So I think that will be the end of it.
Yeah.
We'll wrap it
Biswas,
up.
why don't you write a book on this one?